Good morning, everyone. It's a pleasure to have all of you here in another live stream of Abralin ao Vivo. As you know, Abralin ao Vivo, Linguists Online, is an initiative promoted by Abralin, the Brazilian Association of Linguistics, in collaboration with the Permanent International Committee of Linguists, the Latin American Association of Linguistics, and Philology, the Argentinian Society of Linguistic Studies, the Linguist Society of America, the Linguistics Association of Great Britain, and the Australian Linguistics Society. My name is Magnum Rochel Madruga. I am a phonologist from the Federal University of Minas Gerais, UFMG, Brazil. And today, I'm honored to present this talk given by Marc van Oostendorp from the Mertens Institute of the Royal Netherlands Academy of Arts and Science. Marc is a phonologist, a professor of Dutch and academic communication at the Radboud University of Nijmegen. He has published several articles and books, including Phonological Projection, a theory of feature content and prosodic structure. He has edited the well-known The Blackwell Companion to Phonology, and today he's going to give a talk called Calculating with Sounds, the legacy of Roman Jakobson. Thank you, Marc. Thank you very much, Marc. Thank you also the audience. The turn is yours.
Thank you. I wanted to take the opportunity to present to you, to talk to you about when I can show what I wanted to show. I wanted to talk to you about the legacy of one of, in my view, the greatest linguists of the 21st century, and maybe one of the greatest humanist scholars in the 21st century, Roman Jakobson. And one reason for that, it's now 80 years ago that we were also living through difficult times in most of the world. And Jakobson was, well, he was basically, you could say, kind of a victim of those difficult times. This was, of course, I'm referring to the Second World War. Jakobson, being a Russian, had fled first to the Czech Republic, and then he was basically in 1940, he was traveling all through Europe trying to flee the Nazis, which he barely managed. He was he must not have had a lot of books to his disposal. He must have been almost in self-isolation for most of this time, and still he managed to write a book which I at least consider to be one of the most important books in language studies of the 21st century. It's a small book, it's a little book, and in German it was called Kindersprache, Aphasie und allgemeine Lautgesetze. It was a small book, but it was a very important book. It was a very important book because in this book he presented his view on the feature. Basically, he introduced there the phonological feature. And this is what I want to talk to you about today. I want to talk to you about Jakobson's view of the feature. I'm going to present to you a little bit this little book because it seems to be unfortunately forgotten by many. I present his main arguments in favor of this distinctive feature, one of the building blocks still, I would say, of the formal study of language. But I also give some newer arguments for the feature, as well as some challenges we discovered since 1940 for this particular concept. And then I want to move on and show a little bit of how we can progress from there, from where we are now, how we can take this Jakobsonian program, or at least part of this Jakobsonian program, one step further. How can we understand language even better when we refine the notions which Jakobson gives, and in particular, when we formalize them a little bit more than he did. So this is what you see now is my plan for today. So I'm talking about Jakobson and the feature. I'm talking about some arguments for features which are relatively new or which developed at least after 1940. I present some challenges. I then go into what I call feature behavior and inventory structure. And then I model the system. I want to comment a little bit on this point 4 here, the feature, because what this particular talk is meant to do is, let's say, revive part of the good old structuralist idea of language. Something to this idea, I believe, that language can be studied as a structure. Right, so let's move there. And let's talk first about Jakobson and the feature. As I said, he wrote it in German, and in German it was called Kindersprache, Aphasie und allgemeine Lautgesetze, which means child language aphasia and general sound laws. It was, as I also already said, it was part of European structuralists were more interested I lost the connection, but I think I'm here again now.
Yes, we're here.
Were interested, European structuralists were interested in more in structure, were more interested in formal structure maybe than some of the their American counterparts. And the findings of European structuralism was that sounds and phonemes, so sounds, so vowels and consonants, were first determined to be the smallest units of language, the atoms of language. Now, of course, that meant there would be quite a lot of different atoms, even in any given language. We now know that, well, let's say if a language has a very small phoneme inventory, that still means it has about 13, 14, maybe 12, but not less different phonemes, so 12 different atoms. But there's more structure to that. There's more structure to the inventory of sounds. This is still pre-Jakobson. For instance, if we have a language, so like a toy language with an imaginary small 4 consonant inventory, P, B, T, and D, that there is structure. Those are not just 4 random points in the phonetic space, but they are organized in a certain way. They're organized, in this case, across the dimensions of voicing and labiality. And that's not a coincidence. So it's not a coincidence that if we have a language with 4 consonants, it could be 4 like this, rather than one being nasal and labial, another being creaky voiced and coronal, and the third being guttural, etc. Every sound being different from every other sound in many different dimensions. No, we have 4 different sounds. That means 2 different dimensions, because 2 times 2, 2 binary dimensions, 2 times 2 means 4. So that was the basic insight, but still for people like Trubetskoy, the phoneme would be the elementary unit, would be the atom, and then there would be these oppositions. Now, Jakobson's insight was that if we have these oppositions, then they might be actually the ultimate building blocks of language. So not the phonemes, but the phonemes are themselves bundles or structures somehow organizing things like voicing and labiality. Voicing and labiality, they are the ultimate building blocks of language. They are the atoms of language. So that a B doesn't really exist like that. P doesn't really exist like that, but rather what a B is, what we call a B, in reality, let's say in phonological reality, is a structure consisting of 2 different fundamental units, namely labiality and voice. Now you can imagine that this gives already at least a reduction of the number of elementary units of atoms we have, right? So we have, instead of 4 phonemes, we now only have 2 different binary features. These features have some kind of internal structure. I'm not going to talk much about that today. So 2 binary units, and they give us these 4 different phonemes as a result. The phonemes are not building blocks. They're basically just results of having these 2 different features and being free to combine them in whatever way you want. That would be the idea there. Now, Jakobson's book was called Child Language and General Sound Laws. It meant that he didn't just introduce this concept which has proven so useful in, at least in phonology, but actually also in many other different parts of grammar. He didn't just introduce that, but he also introduced a way of looking at phonology, which I believe to be very modern still, by taking into account many different kinds of evidence. So not just looking at one kind of evidence, but trying to look at different kinds of evidence and then try to see where these kinds of evidence converge. Now, again, you can criticize Jakobson because and he has been criticized because he didn't have a lot of child language data. He didn't have a lot of data on aphasia, but he was going around Europe. Remember, he didn't have a lab. He didn't have anything. What he had is notebooks, but he did what he could. And I think maybe for this reason, so that the evidence was, each different aspect of the evidence wasn't very strong, but the fact that they converged, that showed something. And they converged on this notion of features, and maybe even, at least in his view, on a specific view of those different features. Now that, I think, is still the case, at least optimally the case, for the study of language. Language acquisition, so what he called child language, is still, I think, an important type of evidence for features. Aphasia or any kind of psycholinguistic or even neurolinguistic data is important for understanding the feature. And then, of course, general sound laws, which means typology and maybe theoretical phonology, they're also important in combination with the other 2. Jakobson also drew from other aspects of modern science in his days, like information theory, the idea that when we transmit a signal, a sound signal in our case, what you transmit is only the relevant information. When I say an ah, There's all kinds of irrelevant things about the sound I produce, which have to do with the particular shape of my mouth, etc. But they're irrelevant. And what the phonology is about, what the cognitive structure is about, is this reduced version consisting only of the relevant, of the distinctive features. That I think, well, actually that one of my arguments is going to be that kind of looking at these things computationally is also still important. And finally, I give neuroscience there. I already said one thing about aphasia, of course, is kind of neuroscience. Nowadays, last decade, I guess, there have been a few papers which seem to show that also there's also evidence in our brain that sounds are organized according to features. That if we hear an M and a P and a B, so all labial sounds, there's some kind of region which always seems to light up. If you look at the brain scans of people who say these kinds of sounds. Now, as I said, the empirical basis, you could say, of Jakobson was in some respects necessarily rather weak, not just because of the particular circumstances he was in, but also this was 1940, the 1940s. People just still didn't have all the possibilities for looking at data. We have been trying to review a couple of years ago some of Jakobson's programs, so both on child language and on aphasia, and it seemed to show that indeed what we find in all of those cases is evidence for features, for binary features. Children, when they learn their language, when they learn the sound inventory of their language, when they learn the phonology of their language, the basic phonology of their language, they don't seem to learn sounds one by one. Also, they don't seem to just learn the sounds according to the frequency, so the most frequent sound first, most frequent consonants first, let's say, and then the second most frequent consonant. No, they learn them in an organized way. Once they learn the feature labiality, they can apply it to all sounds, all other features they have. So they learn all combinations of features they have. The data I present here are from a famous database on Dutch language acquisition. It's over 25 years old itself, but still very useful for this kind of study, where because it followed a number of children very precisely in their development. So every few weeks they were recorded by my colleagues, Vickert and Level. What you see here, so here you see some of these children and the order in which they learned the different sounds, the different phonemes of their language. So child 2 started in the onset of the syllable. So the beginning of the syllable started with B, P, T, D. And then in the next session, she learned an M. And then in the next session, she learned an S and a Z, etc. In the coda, the order is slightly different. So we have to separate onset and offset of the syllable here. We're not going to be concerned about that because each of those two paths for each of these children, and as a matter of fact, for all of the children in this entire database, can be understood by seeing that the children learn features. In the first stage, this child has a B, P, T, and D, which means the child has a feature, well, okay, so feature for being consonantal, but we're only talking about consonants here, so I didn't include that in the table below. But otherwise, two place features, so labiality for B and P and coronality for T and D, and then a feature voice for B and D, which P and T don't have. So it has two place features. She has two place features, and she has one laryngeal feature, voicing. So basically, these are two features if we assume that labiality and coronality are mutually exclusive, even for maybe for phonetic reasons. So B, P, T, and D, they're all, so that's basically all the combinations we have, right? So we have two kinds of features, a place feature and a voicing feature. And they can be, if we can say, well, these can be freely combined with the phonetic restriction, then the child has all the sounds which are available according to this system. Now, so the prediction is in the next stage, when she learns a new feature, she's immediately going to apply that everywhere. Children don't do that completely like that. So the prediction of a simple model is the child has B, P, T, D. Now she learns nasality, and then she has an M, a labial nasal, and an N, a coronal nasal. That doesn't always happen exactly like that. So the model, so it's very simple model where you say, well, you just freely learn features doesn't work. As simple as that. Excuse me, there's something. Yes. Okay. So it doesn't work as simple as that. So we need one thing, but we need nothing more to understand the acquisition of these children. And what we need is what is called feature co-occurrence constraints. So we need to add to this, I'm sorry for this, we need to add to this model, so feature co-occurrence constraints are called FCC here, right? So FCC, feature co-occurrence constraints. So when the child learns the feature nasal, she also learns the feature co-occurrence constraints. Nasal implies labiality. Nasal implies labiality. That's what you can see here. So having all the features with free combination, given the feature co-occurrence constraints, gives you the predicted inventory. Now you can say, well, yeah, okay, of course. So you learn all the features and you say you can freely combine them, except that sometimes you say you cannot combine these. But what we found is that these feature co-occurrence constraints can be very simple. They always only need to refer to two features at the same time. So in this case, nasality and labiality, never to three features at the same time. It's same is true for star, voice, velar, which you see here, number 5, star, voice, velar. So that's the opposite. It says voicing cannot be combined with velar. So number 1 says nasal implies labiality. Nasal has to co-occur with labiality. Number 3 says voicing cannot co-occur with velarity. That's the only types of feature co-occurrence constraints you need. So we need two things. We need features which can be freely combined, and there are feature co-occurrence constraints. Furthermore, in learning, what we assume then at least is that the relevant feature co-occurrence constraints can only be introduced the moment you learn a feature. So the moment you learn a feature, that's the only moment when you can introduce nasal implies labial. And later on, the child learns, oh, but there is an N in the language, then it can revoke feature co-occurrence constraints, but that's the only thing which can happen. Okay, well, that's acquisition for you. For aphasia, we found also evidence for features in this, so that it's this figure here, which gives some evidence for that. So when a patient suffering from certain kinds of aphasia, they produce, let's say, the wrong sounds. Now, what you see here, 1, 2, so the 1, 2, 3, 4, 5, 6, 7, what that means is the distance between the sound which is actually produced and the sound which was intended. The distance in terms of features. And what you can see is the fewer features the smaller the difference in terms of features is, the more likely it is that a person makes a difference. You can say, well, that's because of phonetic similarity. I cannot go too much into that, but it must be more than just phonetic similarity. I can just tell you that. So that is a part of that was what the Jakobsonian program was about, except for the general sound laws, right? So, I think the general sound laws might have always been the most important argument for doing it in this particular way, to choose this particular formalization of this idea. There are arguments like categoriality, that we listen to sounds in a categorical way. We don't tend to hear gradual differences. We hear something is a B or a P and not something in between. There's vast, solid evidence for that. Natural class behavior. Phonological rules refer to a class of sounds rather than to individual sounds, and those classes of sounds are easily described in terms of features. And then the notion of feature economy, the old structuralist notion of feature economy. So categoriality, I already said, we see it in perception, we see it in phonological processes. So there's no lexical phonological process in languages of the world where you change a sound gradually according to the context. So if it's lexical, then it's definitely categorical. You change something which is voiced into something which is voiceless. That has sometimes been contested. I just note, so Porter and O'Leary is a famous paper in language saying final devoicing, the process we find in German, in Dutch, in Russian, in many languages, is not always completely categorical. I don't think their arguments are completely convincing. I've never thought they were completely convincing, because basically what they point out is there has to be something. They're not binary. The features are not necessarily binary. There has to be a way for devoiced sound to be different from both a voiced and a voiceless sound. But once we have that, then we're done. And having three different versions is still categorical. It doesn't make something continuous, doesn't make something anything less than categorical. Feature economy is the last thing I want to mention, because it's probably the least known in the modern world. Nick Clements, the late Nick Clements, tried to revive the notion in the first few years of this millennium, and then unfortunately he died. The idea behind feature economy is an observation I just made now about inventories, namely that they tend to be symmetrical, that an inventory of consonants in particular tends to be a square of some, or a rectangle at least of some type. So if we have a P in, so yeah, that's okay. This is a good way to see it. If we have two languages, one has a B and the other one doesn't, and now you have to predict which of the two languages will have a P, then you have to choose. You should basically put all your money on a language which also has a B. So if a language has labial sounds, it's more likely to have other labial sounds as well. So this is Clements' definition. He gave a sound S will have a higher than expected frequency in languages that have another sound T bearing one of its features, and vice versa. So it says T here, you don't see that now. So now you see it. So it have another sound T bearing one of its features. So if you have a B in a language, then it's more likely to also have a P than the other way around. So that's a way of formalizing this observation that consonant systems tend to be rectangular. They're not just individual dots somewhere in the phonetic space, which, let's say, functionally speaking, would make at least some sense to have that, because it would make confusion between different sounds less likely, right? So there's potential confusion between P and B. If we have a P and then a ah, and all different kinds of sounds, then confusion is much less likely. But languages are not like that. Languages tend to be rectangular, so the observation is a statistical one. It doesn't say that there cannot be any holes in those rectangles, and as a matter of fact, languages tend to have those holes, which we formalized by our feature co-occurrence constraints. Notice, right? So the child language Dutch, at least at some point, lacked an N, and that was because there was a feature co-occurrence constraint. So I've given these two different kinds of tables here. So PTFS, BDVZ, well, that's a much more likely consonant inventory than the other one. The other one is not completely impossible, but it's so unlikely that you would be extremely surprised to find something like that, where all sounds are different in all different kinds of dimensions from each other. So I think the Jakobsonian program in this respect still holds. I think there are a few alternatives to it, like gesture theory or element theory, but basically they keep these kinds of properties of feature theory intact, and that particular part of feature theory still holds. There's many challenges as well. The most important challenge, I think, is with the idea that then the features would also be universal. So coronal, labial, voicing, those are the features we saw. Those we will find in all different languages and no others. And so I listed a few problems with them here. So there's a problem of duplication. So because these features, they all have phonetic information, why would that phonetic information also be available in the phonology? Do we need it twice? We need it in the phonetics anyway, so do we also need it in the phonology? There's a problem of outliers. So some languages do have like individual sounds which would require a lot of features which are different from other sounds in the language, or even other sounds in other languages. So people have detected some languages having, let's say, weird sounds outside of the box. That's difficult for having a universal set. It's not different. Well, it's strange for feature theory in general, but it's not impossible according to feature theory in general, because you can have a language which has one feature for just one sound, and then all other features are excluded from combining with that one feature. There's the problem of biological plausibility, at least if you believe that there's not just a universal feature set, but that's also innate. So why would that particular thing be innate? And then there is the big problem of so-called crazy rules. So rules which refer to unnatural classes, to groups of sounds which are difficult to describe in terms of phonetically motivated features. And all of this has led researchers in the last few decades to something which by some of them is called substance-free phonology, where we hold that, sorry, I shouldn't talk so much without showing you something, because then I'm immediately punished, but you're going to see it again. So which doesn't, so substance-free phonology, which says we have the features, we have the formal structure, and that might be universal just because that's how we think, how people tend to think, is the thought is organized, but the concrete substance must be learned. Okay, I'm going to assume that I'm not going to go into that debate, because as I said, as I announced, I myself have been interested in this other aspect of the Jakobsonian program, namely the sound laws, the formalization of this structure. What was a disadvantage for a long time of the kind of program we were pursuing is that we had to say children learn two things when they learn a language. They learn features on the one hand, and then they learn feature co-occurrence constraints, and they learn them at the same time. But we thought, when we have to pursue this Jakobsonian program any further, we can say, well, maybe these feature co-occurrence constraints are somehow part of the features. That's something which I, together with Roberta D'Alessandro, called magnetic grammar. The only thing you learn when you learn phonology of a language, the only thing you learn is the features of the language. You only learn voice, etc. And then they can be freely combined. But these features can have the property that they are uncombinable with other features, or they need to be combined with other features. So we have a set of Lego, and we can freely combine them, but some Legos just don't fit together with other Legos. And we call that magnetic grammar because we took over the old idea that there can be only two such properties, namely one of what we call attraction. So feature F can have these two properties. That's what it says here, right? So feature F can have two properties. It can either attract the feature G, which says, so if the feature F has that property, then it can only occur when there's also feature G there in the same segment, let's say. And when it has the other property, the rejection property, it cannot be combined with G at all. So that was the idea. So that's a Jakobsonian idea, because we say, well, there was something first outside, like the oppositions in old structuralism were outside of the segment, but now we draw them into the feature. We give the feature is no longer simple and atomic, but it has an internal structure as well. So that's the idea we had. That's our way, I guess, of honoring this great idea of Jakobson, right? So, and we have shown in work by Marc van Oostendorp, for instance, has shown that if you take a typological database of segments, all of those segment inventories, right? So all the constant inventories of all the segments in such huge typological databases can be described using these principles. So the grammar, universal grammar, if you want, that only says we can freely combine features. And what you learn is the features of the language, maybe their phonetic content, but also the way in which they can be combined, their internal structure, their attraction and rejection properties. And in order to what shall we say, to prove that, to show that that works, we have tried to build a computational model. I'm showing you here a Jupyter notebook, if somebody knows, if you knows who that is, which it is a combination of, well, somebody out there must know what it means, but so it is a combination of text and computer code. I will make sure that when this video is finished on YouTube, underneath it, we will put a link to this, because this page is also online. But I just want to show you how it works. So it's a combination of computer code which really runs and text explaining the computer code. So this is basically a paper using computer code. So what it shows is, first we have here, so where it says in 23, you see that I made up some toy set of universal feature labels. Again, the claim is not that these are indeed universal feature labels. Those universal feature labels can also be substance free and just be A, B, C, D, etc. Okay. But people will connect A, B, C, and D then to some kind of phonetic property in their language. Okay, since I didn't want to go into that, I've just simplified and assume that the features have some kind of phonetic content, basically universally. So it's not an important assumption for what I'm doing here. I've also, for similar reasons, I've given here a number of segments, potential segments. The first is schwa, so this is where it says in 24. So the first is schwa. I've given their feature labels. So schwa only consists of a feature vocalic, A consists of a feature low and vocalic, D consists of a feature voicing and consonantal, etc. This is just to have, so this is again some kind of toy set of segments. Of course, the real set of segments will be much longer, the real set of features will be much longer, but this is what we need to show everything we have. It's not going to make much of a difference if these sets are much bigger. So what we can then do is we can formalize the ideas I just expressed. We can formalize the ideas, which I do here in 25. We can formalize the ideas of rejection and attraction. This is done here in computer code, in actually Python, a famous programming language, but it's famous among other things for being eminently readable, especially for linguists, especially for anybody who knows anything about lambda notation. So rejection is a function which takes a feature and a domain and says, well, it's false. So if that feature is in the domain, right? So we take a feature and a domain, we take a feature G and the domain, let's say the segment, and then rejection is false if that feature G, reject G is false if that feature G is in the relevant domain. And attraction is the opposite. So it's true if the feature is in the relevant domain, right? So this is grammar. This is basically all there is to grammar for understanding segment inventories. In 26, I give some kind of very small toy language which has only one feature, and that feature rejects another feature. So that would be notated like this. So if the language has a voicing, and the voicing cannot be combined with continuancy, so we cannot have voiced fricatives, which is not uncommon in languages of the world, this is what that would look like. This is what a fragment of that language would look like. And a slightly bigger toy language you see in 27. So here we have 1, 2, 3, 4, 5 features. And vocalic has the property of attracting low. Consonantal doesn't have any kind of specific attraction or rejection property, and similarly for low and continuant. And voicing has the property of rejecting the continuant feature. So it's the previous feature, but now embedded in a slightly bigger, but still extremely small and unlikely and completely toy language. So what we then say is what I give in 29 here. So what's a valid segment? Well, a valid segment is a segment for which all properties, and the property, so property is rejection, attraction, etc., for which all properties are hold, right? So for all properties, all properties of all features hold. So we look at all features, and we look at all the attraction and rejection features. Then we see whether they hold in the segment. If they do, then we have a valid segment. So that's what we do here. And then what this 4S in feature matrix does, it looks at all the sounds, all the consonants we have in our feature matrix. So that was the table of all the different sounds I gave. And then it says whether that particular segment can occur in this language or not. So of our presumed universal set of segments, which of them can occur in our inventory of this individual language or not? Well, okay, schwa cannot occur, A can occur, A can also not occur because we only have consonantal features. But D, T, S, and Z can occur. Notice we get symmetry here, almost automatically and almost by default, right? And all the other consonants cannot occur. For all the other consonants, we would have to learn more segments. Again, I'm going to give this, you can check this on your own. You can change things in this program. You can add different features to the language, and you can play around with it and see how it works. You can even make a full description probably of your own language and see whether this system works for your language or not. I've also built here a function which basically takes now all different combinations of those different features and gives you this different sounds which can be combined with that. And then I've provided a function valid word, which says a valid word is a word in which every individual segment is valid. It doesn't take into account phonotactics. That's a different story. That would be a different talk. I think phonotactics are also properties of features. Again, that's a different story. Well, what I want to show you most is the last little bit where we define some functions which can learn a language, which can learn features. And again, it's very simple. You go through my code, it's extremely simple code, but it's extremely powerful. It can do many different things. If we learn a feature, what we assume, if you learn a new feature, so the child learns a new feature, it means she observes there is apparently some kind of phonetic thing going on which is contrastive in the language, which plays a role in the language. So she posits the feature for that. She posits nasality, let's say. And at first, what she assumes is that nasality is going to attract and reject every feature which she already knows. Attract and reject them. That's what this definition in 35 here says. So we attract and reject every individual feature. Now that's of course absurd. Such a feature cannot exist because you attract and reject the same feature at the same time. So you're never going to be happy, right? So if the feature is there, you're not happy because of rejection. If the feature is not there, you're not going to be happy because of attraction. So the next thing you then do is you go through all the segments which you know, which you learn, every segment sound you hear, and you see, well, okay, so I hear an M, so the rejection property for labiality cannot be true for nasality. That's what you do. So you hear an M, well, you have just learned nasality, now you revoke your rejection property for labiality, right? So, and about the attraction property, you don't know until you hear an N. N doesn't have labiality, so then you revoke that. So the system, in many ways, still works the same as I explained before, namely when you learn a new feature, you just assume it has all these different properties. And then whenever you hear a sound, you observe, well, this property is not true, this property is not true, this property is not true. And once you have heard enough sounds, the system will stabilize. So that's what language learning is. Again, you can play with it here. So in 36, we say, well, okay, we have a language. We update it with learning all the features of an S. That gives us a new language. We have a language which we update with all the features of P, and we have a new language. So the idea is we have a language, so give it here in 39. So we start out with the assumption the language is empty. It has no sounds. It has no features. We are newborn babies. And then you learn an S, and then you learn a P. Okay, once you have done that, well, so 40 says print language. That means these are now the features we learned. And 41 gives us then all the sounds which now the learner assumes the language has. So the learner has only heard an S and a P, but she was going to assume that the language has T, S, P, and F, because those are free combinations of the different features. But then when she learns more sounds, so that's in 42 here, she learns a Z, a B, an F, and now in 43, I give all the new inventory of sounds she has. And you go on and on and on, and the system learns and learns and learns. And in the end, the system has established the inventory. The system is extremely simple. And I would say it's simple in a Jakobsonian way. Or at least that would be my aspiration. I'm not even sure that we can pride ourselves of having reached that same level of insight, but it's definitely inspired by this great idea that even in times of complete chaos, we can aim for finding simple building blocks, simple principles to understand that chaos. Thank you.
Thank you, Mark. Thank you, the audience, for the questions. I will make a few of them. The first one is from Laís Bocomi, and she says, in some translations, like in 1972, instead of general sound laws, the term used is universals. Do you believe there is a difference between them and the terms of interchangeable, are interchangeable?
Well, of course. So, well, I guess that it's a good question. It's an interesting question. I would say the term universal is more general. Let me actually switch this off first now, because I don't think we want to see this anymore. So the term universal is a more general one. It doesn't just refer to the kinds of co-occurrence of features to have. It does, but it can refer to many more things. But I think there is a kind of subset relation, and general sound laws are a subset of things which you might call universals. I mean, we are talking here, we are thinking here about typology, and I guess typology in the end always is to some extent about universals. So I think that's right. So we're talking here about a specific subset of universals, which we then call general sound laws.
Okay, thank you. Also, Maria Bardas from Uruguay, she asks, what's the value of other segmentation, such as the chunk or morphophoneme? How does the notion of phoneme could interact with the notion of time?
Yeah, so I haven't talked about time here at all. So I'm completely ignoring time. And so it is true that we need some notion of time, even in our description of a phoneme inventory, of course, because you can have a language which has a difference between short and long vowels. I'm basically assuming, different from a lot of autosegmental phonology, I am assuming that this has to be encoded in some way as a feature as well. So it has to, this also time, also length has to be some kind of feature, because I believe ultimately everything is a feature.
Yes, great. Another question, also from Maria Bardas, which insights do we get from contrasting comparative linguistics regarding phonological corpora?
I didn't get the last bit. From contrasting?
Contrasting comparative linguistics regarding phonological corpora.
I still didn't get to regarding. Now I got until regarding, and then
I think she's sharing phonological corpora in across languages?
Oh, I see. Well, so corpora are relevant for our research program in a number of ways. So corpora are mostly relevant here for the study of frequency. So I said it's quite clear that children don't, at least quite clear to me or to us, that children don't learn consonants in the order of their frequency. So, but there is, on the other hand, it's also not completely the opposite. So so in languages which have more coronal sounds, it seems to be the case that children start earlier with coronal sounds than in languages which have more velar sounds, let's say. So frequency does play a role there. And in order to observe that frequency, we need to study corpora. But what's probably going on there, I think, is that so frequency plays a role in the order in which you learn the features. So you learn you don't learn a T earlier because the T is so frequent, but you learn coronal earlier because coronality is so frequent in your language. And now this is a prediction which I don't think has been tested a lot, but which you I think can only test if you have enough corpora of many different languages, because the prediction is that, for instance, coronal sounds could team up. So K could be the most frequent sound in the language, but if all coronal sounds together are more frequent than all velar sounds, you're still going to learn the coronality earlier than the K. You're still going to learn T earlier than K. Whereas if the distribution is even slightly different, that's still not going to be the case. So for me at least, so studying corpora here is very relevant for understanding the particular order in which children learning a given language are learning the different features.
Okay, thank you. Another question is, what are the universal physical constraints for the uvular trill and the alveolar trill sound? I think she's asking about universal physical, articulatory.
I don't know. I'm not completely sure that I even completely understand the question. Do you understand the question?
No, I think so. I think she wants to ask if they share some kind of physical constraints, because considering the occurrence in language that are not very common to have, the languages have the same trills, there's trills in a specific language.
Okay, maybe I can say something which is at least connected to this, and this is that there are. I actually very quickly said before I was talking about this language where you have the story language where you have labiality and coronality, and they don't combine. And even maybe that's universal, maybe it's not, and at least it's a universal tendency to not combine these things. But given that what we're doing here is substance free, so it's free of that phonetic content.
Yes.
Any kind of explanation which relates to that is actually relegated to the phonetics. So there's certain kinds of attraction and certain kinds of rejection which are going to be universal or near universal, or which are going to be very strong in many languages of the world. But that's not what I want to understand. So I don't want to understand why certain things happen more often than others, and they are probably related to the mechanics of the articulatory organs or whatever, or other kinds of functional reasons you might give, and they're very important and they're very interesting, but I think they're separate from the main issue we're concerned with here now.
Okay, thank you. Nicholas Roll asks, do you think that suprasegments consist of features as well, I think you have answered, yeah, but for example, tone, intonation, stress, and so on, I think you have answered.
Yeah, so that's at least that's what the program should be. So, well, tone for tone, I think many people would say that already. For length, there's a long debate about whether those are features or not. For stress, similarly, I think so different, because I think it would be interesting to try to pursue the idea that everything you learn when you learn phonology is features, that even something like phonotaxis is featural, which means the difference between an open syllable and a closed syllable is featural. And you refer to this book, Phonological Projection, of mine, where I actually try to work that out. So where I try to say, well, the difference between a language which allows for closed syllables and a language which doesn't is in the kind of features which vowels have, and which can be combined at a higher level with a consonant or not.
Okay. Also, I have some questions for you that considering your talk. So about your proposal on learning, you say that lacks in inventory and phonetic, you just mentioned, phonetic constraints could be considered for a language learner by rejection functions of feature combination. So what is the could be the base of this combination of feature for rejection patterns like phonotaxis and also lacks and inventories?
What could be the base?
I mean, how mind to build a rejection function, because it would be something that is learning in a negative way. I don't know if it's that you mean in your talk.
All right. No. So that's a good point. So you don't have to basically learn anything in a negative way, because you start with assuming. So let's assume we are trying to learn a language which has no voiced fricatives.
Mm-hmm.
Now, so the child first starts. Let's also assume the child first starts with plosives. So the child has learned that there is voicing. So because the child has learned there's a T and a D. Okay, now so the child knows there's voicing. Now the child learns there has to be continuancy because the language has fricatives. So it has learned now a new feature, the feature continuancy. It's learned, the algorithm says, when you learn that, you assume continuancy both rejects and attracts voicing. So it has two properties. It rejects voicing and it attracts voicing. However, one of the two you can immediately throw away because you've just heard an S, let's say. So you hear an S, so you know, well, in this language, continuancy cannot attract voicing because the language has an S, right? So we revoke our attraction of voicing, but we keep our rejection of voicing because we have seen no evidence against that. So what we have now is in our inventory the feature continuancy with the property that it rejects voicing. And you're never in your whole life are going to encounter any evidence that that property is not a property of continuancy, because the language has no voiced. So the evidence for that would be a voiced Z or some other voiced fricative, and you're never going to encounter that. So you don't need negative evidence, right? You only need to, every time you hear a sound, you have to check whether does that sound conform to all the properties of all the features I have. If it does, I'm fine. If it doesn't, I revoke the relevant properties.
Okay, thank you. Now about your impressions of the field phonology. What do you think about the gradients and categorical debate, considering that some people claim that gradient is gradient, like phonetic gradients, is part of grammar and part of representations. What do you think about this debate that is going on for knowledge? Or
Well, so what I think about the debate, what I think about the debate is what I think about any debate. Namely, it's important to have the debate, but I do think that there is at least a recognizable subpart of phonology which is categorical. There have been so many experiments for such a long time showing that for a large number of phenomena in a large number of languages, that must be the case. Does that mean that everything is categorical? I don't know. It's also complicated. So there is I haven't talked a lot about this final devoicing, but final devoicing is actually one of the phenomena where this is going on. Final devoicing is the phenomenon where, in my native language, Dutch, if you have an underlying voiced segment at the end of a syllable, then you make it voiceless. So we have the word for dog in Dutch is hond, which underlyingly has a D, we know because it shows up in many contexts, but I say hond with a T. And so German has this, Catalan has this, Russian has this, many languages around the world have this kind of phenomenon. There have been a lot of experiments showing that in laboratory circumstances, this phenomenon may not be completely categorical. It may be at least partially gradient. But as I said, to me, that debate, as I said before, to me, that debate is not completely convincing because I believe that it doesn't really show that it's gradient. It just shows that there is something in between being voiced and being voiceless. But it can be still three different values. And with three different values, you are still fine. So that is just an example, but that is one of the things which make the debate very difficult and complicated, like any kind of debate in linguistics, I guess.
Oh, yes. And the last question is, how do you see the impact of neuroscience and computational linguistics in the development of phonological theory, especially for the role of representations, linguistic representations, and linguistic computation? So what do you think this could contribute to the field?
Well, I briefly refer to the fact that there seems to be some neuroscience evidence in favor of something like phonological features. So there seems to be some kind of evidence that when we listen to sounds in particular, we tend to decompose those sounds into something which are features. So if we hear a P, you can recognize that somewhere in the brain and there's some kind of labial area, and somewhere there is some kind of plosive area, and those seem to light up. And if you hear an M, the same labial area lights up, but also a nasal area next to that. And that is at least something which can be easily interpreted as evidence for features, or at least as something which we can understand in terms of features. At the same time, my impression, I don't know very much about neuroscience, unfortunately, but my impression is that there's still a lot of things which are unclear in that particular kind of research. So it's very promising, but there's also still a long way to go, I guess. For computational linguistics, well, obviously I have a different kind of position there. I presented something computational here now, where which was based on a kind of classical argument for doing computational linguistics, namely you propose a model and then you implement it to show that it actually works, right? So I implemented it Now I will give a link so everybody can play with it and see to what extent it works, right? So you can actually now easily calculate whether what I say, does it work or doesn't it work, right? So and that is, so it forces you to be maximally precise. That's a very old-fashioned idea of computational linguistics, I know, because it's not about big data or deep learning. So I think for this, at least for this particular domain I'm proposing, basically I think you can show we don't need deep learning. Deep learning is something which is too big. It's too powerful. It's a big cannon. But you can do it with if you can do it with what I showed, namely just a very small set of basically lambda functions, it's much simpler than what you need for that. So maybe that to some extent you can say that if that's right, so if what I say is true, that's also interesting because it shows you something about the limited computational capacity we need for doing at least this particular task.
Yes, okay. Mark, I think we are in the end. We don't have more questions. So thank you very much on behalf of Abralin. And I also now will turn to Portuguese to thank the audience, for the Brazilian audience, and thank you for your patience, your talk, your brilliant talk.
Thank you
very much. Então, eu queria agradecer ao Abralin, ao Miguel e à Raquel pelo convite e agradecer a todos que postaram suas perguntas e estiveram conosco neste momento. Espero que estejam todos bem em casa e que possam fazer seu trabalho e assistir às lives da Abralin. Nós também convidamos para quem não se inscreveu, se inscreva no canal da Abralin para que possa receber as notificações das próximas lives. Muito obrigado a todos. Thank you, Mark. Bye.